Hello, welcome back. In today's video we are going to continue our discussion on comparing derivatives. We have a review question right here. It should look familiar to us. So if you want to pause the video and do this one, you can. I'm going to get working on it. And they give us the graph of a derivative. So I am going to put down everything I know about the derivative graph. If we are above the x-axis, we know that the slope is positive. And below the x-axis, the slope is negative. And who's our slope in the middle? It's going to be 0. But also, because it's the graph of my first derivative, I know a little bit more as well. For instance, I can talk about the second derivative. So let's talk about the second derivative real quick. Up here, where the slope of my derivative is 0, this is where my slope of the derivative, that looks terrible, let me rewrite that. This is the slope of the derivative is 0. Well, the slope of the derivative is just the second derivative itself. So at that point, I know the slope is 0 of my second derivative. So down here, it's the same thing. Our second derivative will also be 0. And at point G, the second derivative will also be 0 as well. Same thing at E. It looks kind of weird to say it, but at point E, the second derivative looks like it could be a 0. It might be a D and E. We'd have to zoom in to find out more about that, but either way, it is considered a possible point of inflection for us. So I have all that information. Now for part A, it says, for what values of f does f have a local maximum? So this is our first derivative test. And so we do our first derivative test. Get our critical numbers. Let me change color here. To get our critical numbers, let me go black. To get our critical numbers, this is where the first derivative is 0. Or D and E, and I can get that from the graph. It looks to occur at B, at 0, at E, and H. So I'm going to do my sign chart. There's my first derivative. And let's see here, from A to H, and I plug in my critical numbers, B, 0, and E. And I'm looking for the signs. Am I above or below the x-axis? So between A and B, we are below the x-axis, so we know that the function there is decreasing. Between B and 0, we are above the x-axis, so we know the function is increasing. Between 0 and E, we're negative, so we're decreasing. And between E and H, we're also back below the x-axis, so we're decreasing as well. We want to know, do we have a relative maximum? And of course, that's where the derivative goes from positive to negative. So we do have that. It looks to be at 0. So we would say f has a relative max at x equals 0, and that is because the derivative goes from negative or positive to negative. Oh, done a bunch of those already. What about concavity? Well, to get concavity, this is our possible points of inflection, our PPOIs. This is where the second derivative is 0 or D and E. And we already found them. Look at that. That's going to occur at C. We already said that at C. Looks to be at the letter B. E also, and looks like the letter G. And I can do this real quick. Make this a little bit longer here. We're going to go from A to H. The second derivative, how does it make my function look? C, D, E, and G. And this time I'm looking at the slope of the derivative graph. I'm going to look at the slopes here. So between A and C, my slope is positive. That tells me that my derivative is increasing. It tells me that my slopes are increasing. So if my slopes are increasing, I'm getting steeper as we go along, and that's the definition of concave up. So between A and C, that's going to be concave up. Between C and D, we're negative. That tells us concave down. Between D and E, it's positive, concave up. Between E and G, negative, concave down. And then the slope is positive between G and H, and that's going to be concave up. So where we concave down, this is where the second derivative, of course, is less than 0. So we can say that f is concave down on the following: C to D, or e to g. And I think that's it. 1, 2. Yep. And that is because, of course, the second derivative is less than 0. And there's our answer. Now, do we have any POIs? Yeah, of course we have some POIs. That's where concavity changes. I'll mark those in red. Goes from plus to minus, minus to plus, plus to minus, minus to plus. Well, it looks like we have 4 of them. So we have POIs at x equals C, D, E, and whoops, that's a weird looking G. What up, G? There we go. G, and that is because the second derivative is 0 for D and E, and the second derivative changes signs. Very easy to do. All right. Ooh, that was exciting, wasn't it? All right, so part 2, that's question 2. Let's get out the review. So for question 2 here, they're giving us the graph of f. And this is a pretty easy question, very standard. We want to determine the signs of the first and second derivative. So when I'm looking at the first derivative, remember this is talking about the slope. Are we increasing or decreasing? In the second derivative, this is talking about concavity. Is it opening up or is it opening down? So I can do that. Ready? For question A, I know that the value of the derivative here, ready? Well, if I draw a tangent line here, it's going to be increasing. It's a positive slope. So that tells me that my first derivative is going to be positive. What about our second derivative? Well, this function here opens up. Therefore, this is concave up. And if it's concave up, that tells us our second derivative is also going to be positive. So let's try part B. B here, ready? Our first derivative, again, that's still a positive slope. And our second derivative, well, this now is opening down, so that's going to be negative. Now, if you want to be like fancy, go, the first derivative is greater than 0, the second derivative is less than 0. That's okay, too. All right, for question C, our first derivative, that's pretty easy. This is a positive slope. Slope is definitely positive here. It's a line. So that's going to be positive. Our second derivative, though, is going to be 0. So let's talk about why this is 0. And it's real simple. There's no concavity. In other words, it's not opening up or down. Right there. So we just say the second derivative value there will be 0. Piece of cake. Easy as pie. All right. So let's keep moving on. Number 4, obviously I cannot number things correctly. Oh, there's number 3, found it. All right, so for number 4, we want to write the equation of the line tangent to the graph at its point of inflection. Oh no, so we need to find where the second derivative here will be 0. Since we know that the point of inflection is where the second derivative is 0, so I got to find the second derivative here. Now you might be asking, why not d and e? Well, if I look at this function right here, there's no place where I'm not going to, even if I take the second derivative, I'm not going to wind up with a denominator there. So when I take the first derivative, we're going to get this 3x squared, and if I take the second derivative, we get 6x. So to find my POI, where does my POI occur at? I just take that 6x that equals to 0. I get x equals 0. So what do I want to find now is the tangent line. Well, what are the two things we need for a tangent line? One, we need a point, so I need to find the value at 0. Well, that's just plugging in here, 0 cubed plus 9, and I get 9. And we need the slope. And this is kind of a cheap one to do, so I apologize for that. Find the first derivative at 0, and I can use my 3x squared. So 3 times 0 squared is 0. So my tangent line would be y minus 9 equals 0, x minus 0. I know what you're thinking. It's kind of a very lame line, but there we have it. Okay, so I hope you enjoyed this video. Go into video number 2, and we'll continue on the lesson. I'll see you then.